아나운서 또 보셔야죠.
Welcome back. We are going to start our first plenary session, which is going to be chaired by Professor T.R. Seshadri from Delhi University, who is also the chair for scientific organizing body.
Hello, good morning. Welcome to the first academic session of this conference. My name is T.R. Seshadri, as it was saying, and I'm from Delhi University. And associating myself with this center is of special significance to me because I have the privilege of having been the first research student of Thanu Padmanabhan. So we have two talks in this session. The first one is by Anjan Anand Sen, and the second one is by Harvinder Jassal. So I would like to invite Anjan to give the first talk on tensions in cosmological observations, hints for new physics.
Okay, thanks Shesh, and thanks to the organizers, especially Professor Sami for the invitation. And this is my first time to the SGT University, and I'm really enjoying, and I believe that next 2-3 days will be really great here. Okay, so so this is the BRICS conference, and as I was talking to Professor Shuchkov, I attended this BRICS conference at Kazan, Russia. It was a wonderful conference, and now this is the second time I am here for this BRICS meeting. So Professor Sami told me to kind of briefly summarize in this next 30-35 minutes about the recent different cosmological observations that actually showed some tensions in the standard concordance lambda CDI model. So I will speak briefly on that. I will speak mostly on the different cosmological observations that people interpret as some tensions in the standard cosmological model. They are an issue of interpretation, and different people see this data and these observations differently. So, so I have my own interpretation. So whatever I will be talking, that definitely sort of a bit biased towards my interpretation. But okay, I try to be more as much general as possible in this regard. Okay. So, so this is the thing that the expanding universe that we all know. So we started with some accelerating universe in the very early time, just after Big Bang. Then there is a prolonged period of deceleration in the expanding universe, which is mostly driven by the matter, or like a dark matter, because baryon has a less sort of component than the dark matter. And then around very close to the present universe, the universe started accelerating, and we kind of the universe, the total energy component of the universe is mostly dominated by dark energy. And it's not very visible, but okay, around that time when this dark energy started dominating a little bit before that, the universe also became inhomogeneous, because most of the time universe in the early time it was mostly homogeneous, but after that the universe, the structure started forming in the universe, and universe became inhomogeneous. So the acceleration of the universe, or the period when the universe is accelerating and is dominated by dark energy, is also where the universe is mostly inhomogeneous, or there are a lot of structures in the universe. And that also affects not only, so the dark energy's implication is not only on the background expansion, but is also on how the structure formed in the universe. Okay, so just a brief description about our expanding universe. We assume that at a very large cosmological scale, universe is homogeneous and isotropic at the space, and that is mostly given by this. We take that this FRW metric. It means here I put a curvature term, but we assume, or we believe, that due to the inflation, if the inflation happens in the very early time, universe is basically the spatially flat. So the only unknown component in this background metric is the scale factor, and it's a time-dependent component or time-dependent quantity. so it has the first derivative, which is related to this expansion rate of the universe, and its second derivative, which is related to the acceleration. So universe is expanding, given by A, and then this expansion has a velocity and an acceleration. This expansion time of the velocity that is actually related to the total energy density of the universe. I mean, when you sort of try to probe this expansion rate, it doesn't kind of distinguish whether we have how much dark matter, how much dark energy, and all those things. The only thing that actually one can go in is all those observables is the total energy density of the universe. And those observables are like, if you take the local universe, you can have supernova type 1a, supernova type 2, measures, the surface bite net fluctuation, those kind of, the Tully-Fisher relation. You can have cosmic tonometer measurement, the baryon acoustic oscillation, or the CMB. So all those things actually can probe the expansion rate of the universe, that is the h. Then we have the second derivative of the acceleration of the universe, or the acceleration rate, which is actually given by this parameter called the deceleration parameter. It is actually related to not only the total energy density, but also the total pressure, the 3 into the total pressure of the universe. And these actually can be probed by different observables like supernova type 1a, the baryon acoustic oscillation, the CMB, and other things. Right? So this is with the background universe, but as I said, that the universe is also sort of a lot of structures, so you have to also consider the perturbation around this background. And at least at the linear level of this perturbation, we actually calculate what is called the density contrast, which is the deviation from the background energy or background matter. So this is the density contrast. And there are few observables that is related to this density contrast. One is the growth factor, which is a logarithmic derivative of this density contrast to the log A. And this growth factor can be measured from different observables, like the Euclid in near future can measure it very accurately. You can measure with this weak lensing measurement or the galaxy surveys. Right? Then there is another parameter, what is called this redshift space distortion, which is related to this growth factor, plus a sigmoid, which is a kind of a normalization of the perturbed universe at some scale, which is the 8 H inverse megaparsec scale. So it's the variance of this perturbation. If you take this as a Gaussian fluctuation, so sigmoid is basically the variance of this fluctuation calculated at a scale of 8 H inverse megaparsec. So this parameter is particularly interesting, or this combination is particularly interesting, because if you look at these galaxies, so there are also the velocity perturbation, or what you call the peculiar velocity, and this peculiar velocity is actually related to this combination. So if you can map the peculiar velocity distribution of the universe, you actually can get an information of this parameter. It's called the redshift space distortion parameter. And this parameter or this combination can be measured from different observations, like RSD, as I said, redshift space distortion, the barrier, the B observation from DESI, from SDSS, and in future from Euclid. And then we have another quantity, some combination, which is the total matter density of the universe, and this sigmoid, what we call this SH parameter. This is a very important parameter, because as we look at the galaxies to weak lensing, the shear of the galaxies that we observe in the weak lensing, the amplitude of the shear or the amplitude of the distortion of the galaxy shape, they're actually related to this SH parameter. So if you look at this weak lensing survey, you can directly measure this SH parameter. So these are the kind of basic parameters that we have, and in recent future, recent past or around present time, we have a lot of observations that are actually measured this expansion rate, especially the expansion rate at the present time, the H naught, this SH parameter, this sigmoid parameter, all those parameters have been measured from different observations very accurately, and that actually shows some sort of a discrepancy at the different observations. So that we will call as tension or anomalies, and I will talk about that. Okay, so these are different observables that you say. You can look at the CMB, you can look at the nucleosynthesis, you can look at the CMB, the sound horizon scale, and the CMB, the distance is actually has the sound horizon scale, the power spectrum of the CMB, the angular power spectrum of the temperature distribution or the temperature fluctuation in the CMB. Then you have, as you grow to the later time of the universe, as the structure started forming, so you can measure the growth rate of those structures, the peculiar velocity, all those things actually you can measure from different observations to actually calculate all those parameters, fine. And it seems that when you put all those measurements together, there's a concordance model, what is a special, I will come to that, what is called a specially fed lambda CDM universe. It actually gives a very, very fantastic fit to most of these observations, fine. So if you take this model and try to fit this with different observables, this model is actually a great fit, okay, to all the data actually. So what is that? So basically after the Planck 2018 observations, this lambda CDM model actually became a kind of a standard concordance model for cosmology. And this model, you have a dark energy which is given by this lambda, and then there is a cold dark matter. Actually, this model has these 6 parameters. What is the amount of baryon in the universe, amount of cold dark matter in the universe, the angular scale of the first acoustic peak, which is actually imprinted in the CMB, the tau, which is the optical depth of the reionization. So after a prolonged period of neutral universe or neutral hydrogen, universe starts with the first star forms, so the universe becomes reionized, and the optical depth of the reionization is actually given by tau. It actually means it's important for this later on the decay of the CMB fluctuation. Okay. Then we have the 2 parameters, which is the AS and NS. These are the primordial fluctuation you get from the inflation, and that actually you feed into the later on. So that this primordial fluctuation we believe is the source of the later on the galaxy structures. Fine. So there are 2 parameters to this primordial fluctuation. One is the amplitude of this primordial fluctuation, which is AS, and the what is called the spectral index or the slope of the primordial fluctuation, which is related to the NS parameter. So this is a 6 parameters lambda CDM model. Fine, and it fits. You can see this this fluctuation in the CMB, which we actually when put in the angular scale. So these are the fluctuations, and these are the points. The red dots are actually the measured data, and the blue line is a kind of a lambda CDM model. Fine, with these 6 parameters. Fine, and these are fantastic fit. Okay, and then from these 6 parameters, you actually kind of derive some of the cosmological parameters that we are interested in that I described earlier. One is the H naught, the expansion rate at the present time. This becomes like a value of around 67. The sigmoid that I said is the variance of the fluctuation at some 8 H inverse megaparsec scale. This value becomes this. Okay, for the timing you can ignore this number, but then also this S8 and omega m, that also you can actually kind of derive from this model. Fine. So these are the actual fitting parameter. These parameter doesn't go into the fitting, but once you have this actual fitting parameter, and with a lambda CDM model, you can actually derive this parameter. Okay, so these parameters, these numbers that are here, is actually for a lambda CDM model. If you take a different model and you fit, then obviously this number can change. But lambda CDM is the most simplest model. It gives a fantastic fit. So we take this model as one of the best models, and these are the numbers that you can get. And as I said, this for lambda CDM universe, if you write down the means what the model is, they're actually governed by these 3 parameters, which is the amount of matter at present, the amount of or the expansion rate at present, which is H naught, and this sigmoid. So if you have these 3 parameters, this simple model with the 3 parameters, it actually fit all these fluctuation in the CMB. We don't need except the other things you have. But just for a lambda CDM model, these are the three parameters up to the linear order of fluctuation that we need, and these are the numbers that you get for this model when you fit with the CMB. Fine. Now, what is this cosmological constant? Zeldovich gave very early that it's basically the vacuum fluctuation, and he calculated the covariant energy momentum tensor of this vacuum fluctuation, which is given by this. And when you use like a homogeneous and isotropic universe, this actually gives you a equation of state P by rho is minus 1. So this is the energy momentum tensor is completely covariant, and this is I think this is the only energy momentum tensor for a dark energy, which is actually covariant at every level, not only at the background or at the part of level. If you take any dark energy model, you write the equation of state, but as you go to the part of universe and you go part of the field, the energy momentum tensor or the equation of state doesn't carry forward from the background to the part of universe. But for lambda CDM, it's a completely covariant energy momentum tensor. But the problem is that, so this you get from theory, from your quantum field theory, calculate the vacuum fluctuation and you calculate this energy momentum tensor. But the problem is that the theory, if you take any reasonable theory, like if you say that, okay, my gravity theory is valid up to the Planck scale, or any other scale, if you go up to the Planck scale, the value actually lambda you get like this. If you take it Gauss scale or electroweak scale or other, you get a little bit smaller value. But the observation demands this value to be this, fine? So the lambda that we are talking about in all those, in all those experiments, and it is fitting with the data, that lambda is nothing to related with the lambda that we can actually calculate from theory, fine? So this cosmological constant in the lambda CDM model for the observable universe has no relation to the physically acceptable field theory, okay? So that one needs to understand. This lambda is that we use for cosmology is a completely phenomenological one, fine? So this lambda CDM model is a completely phenomenological fit. It has no theoretical justification as yet. We didn't find any theory model which can give such a low value of lambda. It has three main ingredients, as I said. One is the cold dark matter, and we still don't know what is this cold dark matter is. Lambda is dark energy. We still don't know. You cannot, till now, we couldn't obtain this value from a reasonable field theory. And it also demands that we take a scale, nearly scale invariant primordial power spectrum, which has this form. As I said, these are the amplitude S and a power or a slope of Ns. This is also that we assume, fine? We still don't know what is the reasonable inflaton field, okay? There is no signature in that, okay? So this power spectrum for the inflaton or the initial scale invariant power spectrum and the Hubble function that we take to fit the data for the background universe, these two are completely fitting function that goes in the CMB or any other observation that we take, they are just a fitting function, fine? But strangely, both of these fitting functions, they surprisingly sort of kind of explain or consistent with most of the cosmological expansion or cosmological observation, like whatever you come from CMB or BAO or type 1a supernova or whatever, fine? So these are very, very strange thing, okay? There is no theory behind both of these two, but just a fitting function can fit a variety of cosmological data coming from very early universe to the present universe is a bit surprising. Not only that, if you just take these numbers, okay, so you see that these numbers, so this model, lambda CDM, they are kind of containing these three parameters, and the number that we get is that these numbers are fixed when you fit this model with the CMB. So CMB was when universe is like 300,000 years old, fine, around redshift 1000, fine. So these numbers are fit around that time. So the model is actually fit at that 300,000 years ago, fine. I mean 300,000 years when the age of the universe is 300,000 years or redshift 1000, fine. So you have a model which you fit or the CMB feed that model or CMB fix this model at that very, very early time. And then this model predicts at each redshift some value of other observable like supernova, type 1a, DL or D or whatever. And it amazingly fits with the data, fine. So in a way, this is a measure zero model because there is nothing you can actually play with. Everything is fixed at redshift 1000, and that redshift 1000 fixed model predict each redshift some numbers, and somehow the observations actually getting consistent with this number, right? So this is a very strange thing. There can be two things that, okay, we are very lucky to have such model, or till now our cosmological data are not that accurate, so that whatever it predicts, the model, is actually fit with all the cosmology or all the observation, fine? So that is the thing. But now, think that as we are trying to get or as we are getting more fine data with accurate data with much more smaller error bar, there are some cracks coming in this model, and my goal is to just to motivate you to believe that these cracks are really real and important and interesting. Now, fact is that if the lambda CDM model is a very good model, okay, and it is actually the best model, then what do we expect? You expect that, okay, I make a more broader model which also contains lambda CDM, and if I want to fit that broader model with all the data, then I should get the lambda CDM because lambda CDM is the base model, so as this broader model also contains lambda CDM, I should get the lambda CDM back, fine? That is sort of, if you do statistics or data analysis, that's what you should expect. But that is also not true. So this is a more later version. In the Planck paper also they put this figure, but now they have a more later version as you have more better data from supernova or BO. So this is the Planck and all BO, but if you take Planck, all the BO and the supernova data, you get this pink line, fine, this pink contour, this pink contour at 2 sigma, and as you can see these points, so they have taken a dynamics which is not W equal to -1 typical lambda CDM, but just take a equation of state which we call a CPL parameterization by these three people, Chevalier, Polarski and Linder. So here if you take WA equal to 0 and W0 equal to -1, you get back a lambda CDM model. So this point here lambda CDM, but you can actually incorporate with this equation of state different scalar field theories actually. So, but as you can see, if I just go beyond a lambda CDA, but this model also incorporates lambda, cosmological constant, and try to fit this model, this lambda actually is out, means like it's just at the border of 2 sigma, fine, which is also unexpected, which is you don't expect, because if the lambda CDM model is the best model, and then you take a model which also incorporates lambda CDM and fit with the data, lambda CDM should fit in front, in between the 1 sigma or at the best fit level, fine. But as you can see that this lambda CDM is actually out around or just at the border of 2 sigma. And interestingly, the region of parameter space is actually allowed, this region. This is a very strange region, because if you want to try to sort of model this region with a field theory, you can't, because in this region, at some point, the dark energy behavior goes to phantom behavior, which is the behavior where it starts coming a behavior of a ghost, right? So if you want to do a scalar field theory, your kinetic energy term is negative, fine. So this region is a very strange region, which is very difficult to model through any reasonable field theory. Now, what is the status of this figure after the recent DESI result? So this is So this is the status now. So as you can see, so as the DESI now has released their data, and you take CMB, the Planck, and then you add different supernova data, whatever is the Pantheon plus or UNC or DESI, their DESI 5-year data. So this is the lambda CDM thing, which with previous data was just at the border, lambda CDM. But now you see that if you take different data, the tension is from 2.1 sigma to this with the DESI 5 is around 4 sigma, fine. So, so this is a very strange thing that we are getting, that these results with the DESI, the lambda CDM is not only out, but we also in a regime where the dark energy behave like a early phantom, late non-phantom, and this behavior is very difficult to model through any reasonable field theory. Okay. Now the question is that whether there is a really new physics beyond the lambda CDM, whether this figure actually points towards that, or is an artifact of some specific parameterization that we use. So I said that we use this parameterization. We use this parameterization to parameterize dark energy or deviation from dark energy. So whether this is, this sort of behavior that you are getting is specific to this parameterization, okay? So that is one question. So we did a little bit of calculation for that, or little bit of study for that. So what we did, we do a different way to parameterize the deviation from lambda CDM. So there's a lambda CDM, the scale factor is exactly, you can solve this Einstein's equation, you get the scale factor exactly like this. So we said that, okay, let's take a scale factor which you just, instead of this 2 by 3, you put a parameter over b, fine, 1 by b. So it's just a small way, or a very naive way to model the deviation from the lambda CDM, fine. And then you calculate the Hubble parameter, everything, you fit with the data, and try to get back the dark energy behavior and the W0 WA plane, fine. And if you do that, your W0, so this is the CPL, so we just take the DESI, Pantheon, and the growth data. So this is the CPL kind of behavior, okay, this is the CPL kind of, as you can see, from the previous plot, so the degeneracy level or the correlation is along this direction. So that is here also, the correlation is along this direction. But if you take this deviation to the scale factor, your correlation is completely different, fine. And as you can see, this correlation gives you a region, the region over here, which is completely quintessent, so there is no non-phantom or no phantom behavior, fine. So whether you get, so the fact is that this W0 WA correlation that we get for CPL is a very specific to CPL. If you go to a different dark energy behavior or different way to model the deviation from the lambda CDM, you actually can end up with a completely different correlation between the W0 and WA, and which actually can give you regime where you have a perfectly physically acceptable regime of W0 WA, which is a quintessence or non-phantom regime, and you can write your favorite scalar field theory or other theory just to model this regime, right? So we are not saying that, okay, this is actually the inverse. What it actually shows that one needs to be very, very careful when we interpret the data with some specific parameterization of the dark energy, because there can be some inherent bias when you take this parameterization or any other parameterization just to interpret the results or interpret the observations, fine? So that one needs to be very, very careful. And so on this, we also did some study with one of my postdocs that just to do a model independent reconstruction of the dark energy behavior from the DESI data as the DESI came, DESI and Pantheon Plus and other data. So we did a completely model independent, so we are not using any dark energy model, or we just take a Gaussian process and try to get from the data the behavior of the Hubble parameter, or this is the kind of a ohm parameter which actually says that any deviation from the constant ohm actually gives you a beyond lambda CDM model. And if you use this Pantheon Plus data with the DESI, the dashed line is the Planck model for lambda CDM, and this region of reddish regime is basically the reconstructed behavior. And as you can see, this lambda CDM model is perfect. There is no deviation or nothing inconsistency one can see from the lambda CDM with our reconstructed behavior, fine? So as you have DESI plus Pantheon Plus, there is no such deviation that one can see, okay? There are no new physics that one can see. But it depends, if you add a different supernova data, which is the DESI 5-year sample, then you can see that here and here, that there is a deviation around more than 3 sigma, fine? There is a deviation more than 3 sigma. So, so again, whether this is, the DESI 5 years has some extra systematics, that also people have been studied. George Estasu wrote a paper, he compared the Pantheon Plus data and the DESI, because if I go to the previous slide also, the most deviation that you get for these green contours, which has a 4 sigma deviation, which is the DESI Y5, so that also has a very, very large deviation from the lambda CDM, right? So our result is also consistent with that in a way that with the deviation with the DESI 5 is kind of around 3 sigma or more than 3 sigma. So it also depends upon which data you get or you use, and whether the data itself has some systematics that we still don't know, fine? I will talk about that a little later in slides, okay? So again, the learning from here, all these sort of exercises is that yeah, there are some results, some data, and you can interpret per data, but while interpreting the data, you need to be very, very careful to choose a model to fit or do other things or use some different data, and you have to be very careful about the systematics of the data and other things. Just blindly sort of interpreting the data, giving some new physics may not be true sometimes, okay? Okay, so this is up to some level that what the lambda CDM model actually tells. Now I talk about the tension that we are having, fine? So already I told you that when we have a lambda CDM model and you feed it the CMB, and then you extract the H naught for giving the lambda CDM model, you get a value of around 67 kilometer per second per megaparsec, fine? But this H naught actually you can measure directly, like what Hubble did around 1930, just from the local observation. It doesn't need any kind of cosmological model. So you just look at the local supernovas calibrated by some nearby objects like CFI or TRGV, means different way you can calibrate, and you can measure this H naught just from the Hubble relation. The distance is proportional to the velocity and the proportionality constant is the Hubble parameter. You can do that, fine. And that people have done, means this is the HST key project called the SHOES project. They have started this project in 2001, and then with time they actually sort of betterment their error bar, so the error bar significantly reduces, and in 2022 they came up to a number is around 73.3 plus minus 1.04. Fine. So this is the number that you get from the shoes measurement using the HST supernova type 1A data with calibrating through the CFID variable. Fine. And this is the Planck number that I showed earlier. It is around 67.4. And these two numbers are now reached a level of around a 5 sigma. So 5 sigma is a number. Sometimes people think, I mean, in the community that it's a number that when you achieve this kind of number is something tells you that maybe there is a real problem, okay, between these two measurements. As I said, this measurement is local measurement. It has a lot of astrophysics in its systematic, but it doesn't it doesn't need to assume any kind of cosmology. This measurement is from CMB, very, very early universe. The systematics are very, very well handled, and people believe that their systematics are pretty nice. We are pretty much good faith on that. But it assumes a model which is a lambda CDM, fine, and they have a discrepancy. So one has to understand that this measurement is based on the physics of the early universe, okay, and this measurement is based on the physics of the late universe in a sense that it's based on the astrophysics of stars. These two measurements are separated by around 13 gigayears, fine, the universe age, fine. Yeah. This one or this one, this is the probability. This is the probability. Okay, so they are really, really hugely separated measurement, fine. But still, they at least agree within 10%, which is a fantastic thing. That actually says that our means whatever we understand in the cosmology is more or less true. Okay, there are just 10% deviation. That's fine. We need to understand that. But at least physics or whatever we do, they're completely. I mean, they're in a good controlled way. Fine. But there is a 5 sigma tension, fine, in between these two measurements. And so this was in 2022, this measurement came, fine. But now we have a lot of measurement from this local universe, fine. The Planck measurement is there, but there are a lot of local measurements are there. So this is the Planck measurement. This is the Pantheon and shoes that I showed. But now there are pretty much different measurements. Some have larger error bar, some have smaller error bar. Okay, these are from basically the near-infrared supernova. Okay, these are optical supernovas. Then there are measurements from type 2 supernova. These are through the surface brightness fluctuations of the galaxies, okay, SBS, so they measured these. These are from the what is called the fundamental plane. I don't have time to explain, but okay, these you can actually from galaxies you can do this thing. They use the deci results and the distance to the coma cluster, and with that they get a H0 value, okay, this is a recent paper. And these are from the Tully-Fisher relation, where you have the orbital or the rotational velocity of the galaxies is actually correlated with its brightness, so you can measure these velocities and you can get the brightness, fine. The interesting thing is that if you take all these numbers that which we have in recent past, actually the numbers are giving, most of the numbers are giving, their error bars can be large, but the central values are giving a larger value than what shoes are giving, fine. So that is interesting in a sense that your local measurements are mostly consistent. Yeah, it's not that you get here 73 and then you take another local measurement with another completely different calibration, you get a value 67. No. So all the local measurements are actually sort of peaked around 73, 74 with varying error bars, whereas the Planck is around 67. Yeah. No, yeah. Model independent is cosmological model independent. Yeah. Means obviously there are a lot of astrophysics model that you have to assume. Fine. When I'm saying model independent, it's the model independent in a way for cosmology. I don't have to assume any dark energy model, lambda CDA, whatever. Fine. So that is the thing. Okay. So that is a very interesting thing. So you need, because when this result came, people say no, maybe there is some, because there are a lot of systematics involved. We still don't know exactly the calibration of the CFID variables and other things. There are a lot of dust things. There are supernova progenitor that he is saying that whether we still don't know those things. So still we don't know those kind of things. But these are completely different things, and you can get this thing. Okay. And these are also H0 from the strong lensing, which also gives the value of this. Okay, so this is also interesting. So And I will come back to this pretty soon. Some interesting things over. Now, this is also another tension, which is the S8 that I said, the S8 measurement. So, Planck actually get a value which doesn't do weak lengthening, but as you feed the model, you get a value of sigma 8 and omega m naught for lambda CDM model, and you get a S8 number. It's a derived number, and you get a value kind of like that. But at the same time, now you have a lot of measurement of this S8 number from directly weak lengthening experiments, right? Whether it's a KIRS or this, DS, or okay, there are a lot of weak lengthening measurements is there. Now, Euclid will come with that. And all these numbers are around like a bit low, fine. And this tension is roughly, it's not reached up to around 5 sigma, but the numbers are roughly around 3 sigma. So this also there is a tension that we have for this S8, fine. And if you want to try to see that what are the model, I am not going to talk about the model. There are a lot of models people have talked about which actually can solve these two tensions simultaneously. There are obviously a lot of question mark on that, but it's a very nice paper by Eleonora Di Valentino in CQEG, where he said that like models which actually solve the tension up to 1 sigma, then 2 sigma, 3 sigma, there are many models are there, fine, okay. There is also an interesting tension that came after the James Webb results, which actually says that it actually measured a few galaxies at very high redshift, which are heavy, which are very massive, fine. So if you take a lambda CDM model and try to find out, and you go to the galaxy formation or the structure formation, at those redshift, getting those kind of very massive galaxies is not very easy. For lambda CDM, you don't get it. You can get it if you get a number of epsilon, which is actually, because the galaxies are formed from the intergalactic dust or the baryonic mass, not all the baryons actually form the galaxies. So usually, if you take your low redshift observation, you get it in epsilon, which is actually percentage of the intergalactic dust or the baryons that actually form galaxies is roughly 10-20% or 25%, fine. But unless you go to a 100% kind of thing, that all the baryons that are available are forming galaxies, there is a very, so these are the two numbers that two galaxies that you get at 9.1 and 7.5, fine. And these are the kind of what the lambda CDM predicts. So this is the numbers, or these are line when you have the 100% conversion of the baryon to the galaxy. So unless you go to that number, okay, it's very difficult to, because the actual or what you expect from the standard galaxy formation data at the low redshift is basically kind of this, okay, 10%, 20%. And these numbers or these observations are pretty high, okay. You get a very massive galaxy. So this is another sort of things for the cosmological model in a way, because if you look at this lambda CDM model doesn't predict such kind of massive galaxies at very high redshift. Maybe you have to change your astrophysics, or maybe you have to change your cosmology, okay. And this is another result, same result at redshift 10, fine. So this is the lambda CDM model, because W is again WA is 0, so the red line is lambda CDM model, the data is something like that, right? So there is a problem. There is also a problem that JWST not only sees very massive galaxies, they have also seen very bright galaxies at the high redshift, right? So that is also that you don't expect from lambda CDM model. So if you look at, so this is the redshift 10, this is the redshift 11, this is redshift 16. So if you take the redshift 10, this is a gray band that you are having over here. This is basically what we expect with the standard astrophysics and assuming a lambda CDM model, fine. And if you take to redshift around 16, so this is the tension is much more prominent, because this is the region that you expect from lambda CDM model or standard astrophysics, fine. This data is still a little bit of problematic, because still people don't sort of this redshift that is 16.5 is still not confirmed. This is a photometric redshift. One has to confirm with the spectroscopy. Still is not confirmed. But these two numbers are confirmed, and they are actually pretty much problem with the actual prediction from the lambda. So the previous one is that you get very massive galaxies, and here you get a very bright galaxies, fine, which also you don't get from standard lambda CDM model. And these are some other redshift 12 or redshift 15. And as you can, this dotted line is basically when you have all the masses baryons that are converted to the galaxies. Okay, so you get this number, but actual things are basically these blue lines, and you are starting getting data. Like you can see, the data are more going toward the number where all the baryon fraction are going toward the galaxy, which is very unlikely. So so yeah, so that is also a problem that you get, or a tension or anomaly, whatever you call, to the JWST model with the lambda, with the cosmology. There maybe one can explain maybe at some point to the astrophysics taking into the cosmology, but this is a problem with these things, right? Okay. Okay, so these are the problems that we have. But in recent times, we are also trying to find out some issues, or whether you can there is a breaking of the lambda CDM, like kind of localizing the missing physics to the consistency check. So what we actually try to find out, that if lambda CDM is a correct model, and these parameters that I described, that H naught parameter, omega m parameter, sigma m parameter, these are the constant parameters, fine. So if you have a model with some constant parameter, and you get these parameters at different redshift, if the model is correct, then you expect these are parameters values that you get, the constant, they are consistent within the error bar, fine, because they are constant parameters. They should not vary with the redshift, fine. So let's say I measure this parameter, this set of parameter at redshift 10, and I measure this set of parameters at redshift 1. You should not expect these two values of these parameters differ like 2 sigma, 3 sigma, fine. They should be within the error bar, that should be consistent, fine. So that is the consistency of the lambda CDM model itself. So before going that whether lambda CDM is a better model or another ABCD model is a better model, let's try to look at what are the consistency check of the lambda CDM model. So that we try to find out. And the first hints came, that the plot that I showed previously, and the holy cow result, the 6 strong lensing things. And if you look at these 6 strong lensing, there are H naught measurement. That actually H naughts are actually varying. Okay, the numbers of H naughts are actually varying, right? And we take all the H naught measurement, all the Hubble parameter measurement from different observations, fine, that is there, you can look at this paper, and we get the Hubble parameter at different redshift also, and you get the same kind of different binning, you get a different numbers, and if you try to see that these are the numbers, and if you see that what is the trend, you see that this trend, that it is not a constant, is basically null hypothesis is basically around out by 2.1 sigma. So there is a trend that the H naught number is changing with different redshift around 2.1 sigma. It's not a very big number, but still there is a trend, okay? And if you can do it the same F sigma measurement, so if you take the F sigma data, you bin it at different redshift, try to get the values of the S8 parameter, and as you can see from different binning, this S8 parameter is actually varying. And if you take this kind of point, this bin and this bin, they are actually differ by quite a good number of sigma, 2, 3 sigma roughly like that. So these are the some plots that we have, okay? So we get the binning that you take all the measurement of redshift 1 or redshift greater than 1 or less than 1, and you get the S8 numbers or the sigma numbers, and they are actually out by around 2 or 3 sigma, right? Which is a very strange, because within the lambda CDM is a correct model, these numbers are constant, they should be consistent within error bar, fine. And same thing these people from 2 different observations. One is using the SGT effect, the SPT, another is the Mike, and here is the Lyman alpha. This is around redshift 2 or 2.3, and this is redshift around 0.3, 2 different redshift, and their sigma measurements are actually out by 3.3 sigma, fine. So this actually says to these parameters which are constant in lambda CDM model, they are actually varying with redshift. They are not consistent actually. And these also now with the latest ACT DESI results, you can see these are the kind of numbers they got. They are actually varying. So this number that you are saying, they are given the redshift, different redshift. These numbers, these points are actually kind of running actually, fine. This is from the Erosita. And as you can see, these are the numbers that I got, okay, for this S8 number, and they are also with the redshift. They are also changing, fine. So we take this clue, and this work is now on preparation. So with one of my postdocs, so we are trying to take the SDSS4 EBOS reconstruction with a completely model independent way, and we try to get the numbers from there like H naught, sigma H, omega m, all those parameters for lambda CDM model. And as you can see that H naught number from high redshift to low redshift, they are actually sort of changing, fine, okay? If you take the S8, these S8 numbers are actually changing, fine? So these are actually hints that there may be some breakdown of the lambda CDM model, because the parameters inside the lambda CDM models are not constant, they are running parameters, fine? So these are the sort of anomalies that we have, or results we have. for the lambda CDM, assuming all these models. So all these tensions are there. I just take 1 minute Shesh just to say just one slide whether there is some new physics which people never thought of. Fine. So this is a very interesting plot by these people in the physical review D when the Desi result came. So as I said, the Desi results has a early phantom and a late non-phantom universe. Fine. So if you take this non-phantom behavior from the Desi data, Desi chain, and this non-phantom behavior, you try to find out that if there is a scalar field, what is the behavior of this scalar field for the non-phantom part at the late time, fine, and try to reconstruct the potential, fine. So they reconstructed, and there's a very, very interesting thing they got. Now other people are also considering it. Is the potential has a minima which is negative. Okay. So this is the Desi results, late time, the non-phantom behavior. You get a region of the potential. So now the scalar field is rolling over here, okay? But with time, the scalar field will actually settle at some ADS minima, okay? So that is there in the Desi result, fine? And then, this is also in preparation. We are doing this thing. We are trying to reconstruct with all the different data combinations. So this is with Planck, Desi, and Pantheon. And if you take the deceleration parameter behavior, it actually shows that, okay, the early time the deceleration parameter is around 0.5, which is the matter-dominated universe. Then universe start accelerating. But the Desi results is actually saying the universe, this acceleration is a transient acceleration. So this Q actually going to a positive value in the future. So these are not important today because, okay, we cannot observe today anything in the future. But these are giving important hints for the model building, because you need to understand that if you want to do a model building, that model building should have a transient feature, okay? So this is from the Desi data that you are getting, okay? And there are some string theories. They are actually taking some ADS model and they try to fit, and they actually got results. This is the blue region, okay, which is actually having a minima which is ADS, and that region, the lambda CDM is out by around 3 sigma, 3.5 sigma. So these are very, very interesting things that are coming in the data. In near future, I believe there will be more to it. So I just keep. So these are the conclusions. So lambda CDM has been very successful, fine, especially after the Planck 2018 result. But it's difficult to motivate theoretically. That is always been the problem. Now there are results are coming from different observations like Shoes, JWST, DESI, DAS, all those things. They are giving some hints that there may be some breakdown of the lambda CDM model. But as I said, that one has to be very careful, because most of the conclusions are drawing, or people have got the conclusion from assuming some particular parameterization. So one needs to read a more model independent way to get the signal of breakdown of lambda CDM. And there can be a problem with our fundamental assumption, like whether the Einstein GL is a correct theory, whether our assumption of spatial homogeneity and isotropy is correct, whether the dark matter is spatial-less, whether we have inflation in the early time that till now we have. So all these things, I think now is a very important time to probe again, and that can, with the data, and now the Euclid and other data are coming, so there's a very interesting time for cosmology. And as like Einstein says, if you can't explain it simply, you don't understand it well enough. So thank you very much, and I can take questions.
Thanks a lot, Anjan. Nice talk. Questions?
Let us say if I come up with a cosmological model with a motivation to resolve the Hubble tension. So if I estimate the parameter at 0, the elevation of the Hubble tension can be due to the best fit value or due to the error bar, increased error bar, right? So is there any possible way to account the decrease in Hubble tension is due to the increased error bar or not? Is there any possible?
Okay. So
that is important.
So let's say I take a model, very simplest model. I get a number of H naught with some error bar. If you now make the model more general, you add more parameters. Usually your error bars, so your base fit model remains around the same. Your error bars getting inflated, and you say that I solve the Hubble tension. This is not actually, because this is actually as you put more error bar, more parameters, you put more uncertainty in your model, so error bar gets inflated. So if you really want to see whether your model actually solving the error bar, okay, that you need to see that whether the central values are moving, and at the same time, whether the model compared to other model, okay, how it fares when you do the fitting. So in that sense, you have to do some Bayesian evidence calculation and other and try to see whether this model has a better fit to the data or not, fine. So just keeping your central value same, you get the central value same and you get the error bar inflated by 2%, 3%, 4% and etc. is all the Hubble tension. This may not be a right approach, okay, that because then if you take another data set, maybe you actually your the central value remains the same, but as you put more data, your error bar start decreasing and you are in the same problem, fine. So if your model really solve the problem, you should at least put 1 to sigma move of your central value in a way, yeah.
Okay. Can I ask one more question?
Okay, the JWST results shows that you have a very high galaxies at very high rich. But then you are also saying that there is a H0 which is also varying. H is varying, right? H is varying is kind of, we know it. Okay. Now, at very high redshifts, when you have these, if I change the models, have people said whether it can actually give rise to such galaxies for other models?
No, so what you are saying is that whether with some other cosmological model, you actually get these numbers for the JWST thing.
Yeah.
At the same time, you also keep your H naught, that thing, fine? Yeah, that's a very interesting question. People have tried, like one of the solution of the H naught tension is the early dark energy model, fine? I mean, I don't have the time, but this early dark energy model try to solve the H naught tension by putting some extra or some another in accelerating period at the very early time, okay? And then the later time remains the same, like the same lambda CDM model, but at the very early time you just sort of give a kick in the H and you solve the H naught tension. And now they try to find out that whether with this kind of model I can actually calculate the observable like JWST and I can get this number, fine, whatever. They tried it. It's not exactly they can do because if you try to do that, you get some kind of sigmoid value that you need that actually sort of spoil your CMB. Okay, so those kind of problems are there. I mean, we did some models with like an ADS, and somehow we managed to do that. So we put the model with the Planck, we get the base fit number, so the Planck doesn't get any spoiled or anything. Take that model now and then try to get the numbers from the JWST, and we get exactly those numbers, right? So in a sense, because these models with ADS kind of model has a prediction that it gives more growth at the early time compared to lambda CDM, fine? So these has some. So yeah, so I mean, this is not the end of the story, but definitely you need to see that whether the JWST solve a problem that you are solving, whether it actually kind of solve the other tensions also. That, but yeah, so still we are doing in that way.
Yeah, thank you for a very nice talk. So I was just have one question. So there are lots of modified gravity proposed, right? I mean, Eleanor's paper and the other. So I am asking that for very modified gravity, it is not uncommon to see that you can shoot out the Hubble data, but the Cepheid calibration or the Chandrasekhar mass which we do, that could also get shifted up. I mean, it doesn't guarantee that it would be sigma 5.
Yeah, definitely. Because I mean, there are also people have used the kind of a transition like the variation of the G, I mean, the Newton constant at very, very low, I mean, late time or around the in the galaxy scale, right? So, yeah, so it can be that because still there's a lot of uncertainty in the Cepheid calibration, in the PL relation, right? And whether there is some astrophysics that you are missing, and then that missing astrophysics can give you a different PL calibration, and that can actually definitely that can be that is the astrophysics side, right? For the time being, I'm not sort of concentrating on the astrophysics side. But if you talk to those people, they believe that that kind of thing, like that, because it's a 10%, fine. So the amount of uncertainty you have till now, or you can expect to do, to like this kind of thing, that you change the G or change other thing like supernova studies or supernova physics and other, or CFEED calibration thing, that can, if I mean, I am not an expert, but what I mean, what I felt is that they think that there is still now there is no such model that can actually give you this 10% shift, okay, if that is there, So yeah, but that is definitely something that one should do, and people are doing that. It's not that.
You show us the list, the
Yeah.
long list of various modified theories. Could you comment, namely this list? Could you discriminate some theories or say,
It is very difficult, but I would say, as I said, the most I think talked model and people studied is basically this model by Mark Kaminkowski and his students and collaborators, which is the early dark energy. Fine. So this is a model where they put some before the recombination, they put another accelerating epoch. So you see that, I have a H is actually coming, fine. I need and the lambda CDM give a H at present, fine. So how this H can be modulated, fine. One thing is that I just put the initial thing high, so that then it comes to this thing, so the initial value high, so that then you take the normal value and you get a higher H, fine. Or you go a late type. So the early dark energy is basically that you put a early dark energy behavior before the recombination that actually give you a kick in the initial H naught, initial H value, and that can be now getting there. So this early dark energy is, I think, like the Schultz team also or whatever, I mean, they take it very, very seriously, fine. But people have also shown that this early dark energy a lot of problem in getting CMB data, quick lensing data and other things, fine. So I would say this is one of the, I don't want to say which is good model or bad model, but this model is the most talked model, okay, that's the early dark energy. Then there is a model like, I would say that there is a model like phantom crossing model, okay, where people take the late time behavior, where there is a crossing of, from non-phantom to phantom or phantom to non-phantom crossing. These also give you a reasonably high H naught, okay. So these are the model, and so as I said, if you take with the statistics, all these models that we have over here, they actually release the tension less than 1 sigma, okay. These are the model where the tension is still around 2 sigma, and these are the model which call is promising model where the tension is around 3 sigma or more, right. So now you think that which, but if, all these models have problem, okay, but at least there is a sort of a around the statistics, they actually, Eleanor did a very fantastic work who's actually doing this thing, but I personally don't want to, because there are some models myself, there are models people of my collaborator and other things, so I don't want to put any comment on that. But I can talk about you personally at some point.
Yeah, a nice summary. Two related points. Okay, first of all, as long as progenitor of type 1 is concerned, it could be actually significantly different than conventional 1.4 solar mass. Actually, my student Zinia also will be presenting in one of the parallel sessions, I think tomorrow. Depending on the physics, it could be varied. Even I was telling you, TRG also trying to find out. And if this is the case, actually, mathematically speaking, it could be reduced. 73 could be 67. Okay, that's a different story. What I don't also understand, maybe it is already there in your talk, when you explain nicely also that H variation with redshift, that also is cosmological model dependent, right? Because when I compute
Okay, that is not H variation, that is the H naught number. Right?
Sorry, H naught number,
and
yes.
that is typically for the lambda CDM model. So what I am saying here, that if you
Yes,
take a
to this
lambda
H naught
CDM model,
itself.
H naught is a parameter in this model, it's a constant parameter. So this number that you get from different redshift bin should be consistent within some statistics, fine? Like 1 sigma, 2 sigma, whatever your favorite limit that you get. But what people are getting is basically this H naught number taking different redshift bin is actually changing and changing roughly 2-3 sigma, fine? So that should not be in a model. So if a model is a correct model, that should not happen, fine? That's but whether that thing is also varying for other dark energy model, I don't know. But at least for lambda CDM, this trend is there, at least at this moment. Whether this trend will go on later on with more specific or more refined data, I don't know. But for your first question, I actually didn't have the time to show, but maybe just 1 minute if shares. So this is a very nice plot. This is the thing that this Dhawan, Sunil Dhawan, Ariel Gubar, and they said. So you see that this is the W0 WA, this is the W0 WA contour that I showed. And then you see that they have actually considered different systematics, fine? And try to see that which direction this thing actually goes. So if you go to later on and you sort of reduce your systematics to different things or the other unknown things, you actually can see that which direction these things can go. In fact, your phantom behavior can go across. Maybe the phantom behavior is basically that there is some unknown systematics is there, and if you refine that systematics, you actually get a non-phantom behavior, maybe, fine? So these kind of studies is nowadays very important because you really have to see that what are the unknown things that you know astrophysics or otherwise, and that can influence your cosmological inferences.
So basically, yeah, I just want 10 seconds. In place of only attacking lambda CDM, I'm basically trying to say there are a lot of unknown or anomaly in astrophysics side also.
Completely agree, completely agree.
Anjan, I would like to ask you a question,
Yeah.
maybe something very stupid. Is it possible that the scale of homogeneity of the universe is actually much larger than all the local measurements you're doing?
Yeah.
There's a big gap between the local measurement redshift and the CMB. Maybe the homogeneity is being achieved in that transition.
And then how it can solve the H dot? Like
Also because all these things, I think it is because of local, void or local density perturbation, which is, because it basically has to do with redshift. It can be Doppler or whatever. Suppose the local one is mixed up with more Doppler.
No, yeah. So that's true. So I understand. So you are saying the local redshift measurement is contaminated also with the peculiar velocities. Now whether those things are you are calculating these peculiar velocities and see that okay they are more homogeneous, so the peculiar velocity corrections are smaller and all those things, right? Definitely. So maybe I can yeah. So you can see that there are all these systematics are there, including your peculiar velocity value. I mean maybe later on you can see, and they have actually reduced those things, those uncertainty. Fine.
So what I'm saying is, suppose you have homogeneity on larger scale, as you are going larger and larger, it is gradually merging to homogeneity, and that's why you see that Hubble H naught decreasing.
No, that's fine, but how much larger scale? So you have to see that your structure formation starts, so you have to have this inhomogeneity there. So you have to see that whether that thing can solve your 10%. At this moment, people see that it's difficult to solve that 10%, but okay.
Thanks a lot, Anjan.
Yeah.
So we have the next talk by Harvinder.
Okay. It's difficult to give a talk after a very comprehensive review. So I was deleting my slides as Anjan went on, but didn't quite complete all. So I'll take a different approach to a similar problem that he talked about. And I, of course, since I made this talk, I put some review slides and I see that there is a varied audience and I hope some students are interested in this topic, so I didn't quite delete all the slides. And this is my first time I'm speaking in a BRICS symposium, so it's quite special. Okay, so I'll basically, the title of my talk, as I mentioned, is a critical reanalysis of low redshift cosmological data sets. But I will talk briefly about what I'm going to basically what all is the motivation to this. So this is a very famous figure which is for the last many years has been shown in almost every cosmology talk. And you, as Anjan also mentioned, the universe began with a big bang, underwent a very fast expansion phase, namely the inflation, which solved the horizon and flatness problem for us. So these are CMB photons, very early universe. Baryons and photons were very tightly coupled via Thomson scattering. And as the universe cooled down, the photons decided to abandon the baryons, and they came to us like the CMB photons. After that, we entered the dark ages when nothing could be observed. There are no structures. Of course, there is radiation, which we can't observe. And as soon as the first structures formed, the universe became transparent, and all these structures you can see and observe. And currently, the universe is undergoing an accelerated expansion phase. Okay, and these are the equations which we work with. This is the speed of the expansion of the universe, this is the acceleration or deceleration, and this is the continuity equation. And from here, as Anjan also mentioned, you can see that if the universe has to be accelerating, this term has to be negative, so you need some sort of a different kind of matter that we are used to drive this acceleration. Okay? And this employed a large number of people into modeling these things. And the most elegant, of course, is the cosmological constant model. I'll say it's the most elegant. And I'll basically try to motivate why we should not kind of abandon it as the best model so far. Okay? So this is the cosmological constant model. And the energy density of the universe remains constant. And if the energy density remains constant, you can see that the pressure has to be minus rho by minus the pressure to energy density ratio is -1. So you need an equation so you basically get a negative pressure term. It elegantly and very easily drives the expansion of the accelerated expansion of the universe. And here we are. So what are the parameters that I will be talking about? The parameters, if you are talking, are the current amount of relativistic matter in the universe, the current total matter, which includes the dark matter and the ordinary matter, which we are made of. This is the curvature term, and this is the cosmological constant. And if you just invert it, you can basically, I joke that you can just invert it, is the vacuum energy density. Okay. Now this is, this term will usually drop because we have from CMB observations reasons to believe that universe is spatially flat. Okay, so that makes our task simpler. And the energy density of the relativistic matter, which includes radiation and neutrinos, is very, very small. So basically we work with these two terms. And of course there is the Hubble parameter and the tension which comes along with it, which I'll talk about in a bit later. Okay. And another parameter which because of this has been introduced is the pressure to energy density ratio, which is the equation of state parameter W. Okay. So we have omega matter, this is the fraction of matter in the universe, omega lambda or omega dark energy, if you want to call it that, Hubble parameter, and W. So these are the constants we try to fit with observations, various different data sets, whatever. If you talk about supernova observations, you have these parameters to worry. And if you talk about, if you are looking at the CMB observations, there are other parameters which Anjan also listed, like the optical depth, spectral index, the omega dark matter, omega baryons, scalar to tensor ratio, and number of neutrinos, their total mass, etc. All these can be constraints from the CMB model. In this talk, I will only focus on the energy density, or basically the fractions of different components of the universe which drive the energy budget of the universe. And we know today, this is the, when I say matter, I mean this sector, which is just 30%, and we are dominated around 70% by the unknown component, the dark energy. And not only is there, it's dominant. Okay? So we have to worry about what exactly this is. Okay? Okay. Although it was supernova observations in 1998 which gave conclusive evidence that there is something like dark energy. Basically, objects are fainter than what you expect them if there is only matter on it. There were earlier indications. In fact, very recently a paper also came about history of dark energy before it became dark energy. And even from large-scale structures and cluster of galaxy, you knew that there is not enough matter in the universe to basically have a closed universe, or rather in the sense that it would make the universe stop its expansion. So at that time also it was thought that the fraction of matter in the universe is around 20 to 30%, and they were quite right. And in 95, there are many papers which basically from the large-scale structure data trying to indicate whether we need something like the cosmological constant. And very recently, this review is a very nice review. If you are interested, you can take a look. And this inference was made in some papers in 95 and 96. And in fact, as early as 90 also, there were papers who were basically saying that, oh, there is something wrong and we need a cosmological constant kind of thing. In 98, there were 3 independent groups which showed that from observations of supernova of type 1a, that universe indeed is undergoing accelerating expansion. And this was return of the cosmological constant, which has had a very bad history or checkered history. It came into being to explain static universe, but then it was dropped where it was confirmed that the universe is expanding. And later, now we need it. It solves not only the problem of acceleration, it also solves the problem of age of the universe. Okay? Of course, the fine-tuning problem is there, and that fine-tuning problem led to formulation of various dark energy models, which include models which are based on assumption that dark energy is a fluid. This parameterization CPL has also been shown in the earlier talk. There are various parameterizations. The reason I list them here is the following. Number one, this parameterization allows for a slow variation at low redshifts. This allows for a larger variation at low redshifts. And this is also from other parameterization. And there are two. This is the current value of the energy, of the pressure to energy density ratio. That is the equation of state parameter. This is its variation. Now look at it carefully. The range of these parameterization basically encompasses any type of function you may have. Okay? So it gives you a parameterization. Alternatively, you have various dark energy models which are scalar based on scalar fields. You can have quintessence models which are canonical scalar fields, and if phi dot is small, you can have an accelerated expansion of the universe. You can have tachyon, non-canonical scalar fields, tachyon models. Here also, if phi dot is small, you can get a negative equation of state parameter. And similarly, there are embarrassingly large number of models, and the author of this very nice review is sitting in the audience, and there is also a recent one in 24. Okay, so you can see if you pick up a favorite model and work on that. Okay. However, let's now come back to observations. Which observations and why do we need more and more observations is what I'll try to motivate in this. Okay. So these are in supernova cosmology project. So if you see here, there are 5 supernovae. If you can see it at the back, I'll read it out for you. 5 supernovae at redshift around 0.4. And you can see pretty much this is omega lambda, this is omega matter, pretty much this big range is allowed for. You add just one supernova at high redshift, Z.83, and your allowed range at 1 sigma and 2 sigma shrinks to a very small value. Okay? Now, this is around 22 supernovae, and you can see you get better and better constraints by coming from here to here. This is the more recent picture from the supernova cosmology project, and there are other CMB and BO data which have been plotted over here, and it's a combination of these orthogonal constraints which is giving us this tiny range in the allowed range of parameters. Now why do I put this over here? Now if you notice that whatever is the range which is allowed over here is the prior over here. So you're actually, these are very, very small compared to these constraints over there. So as you go here in the timeline, you are getting better and better constraints and cosmological constant model with omega lambda around 30% and omega matter around 30%, omega lambda around 70% is right in the middle of these constraints. Okay? This is one motivation. And these are CMB observations through the years. And as you can see, pre-WMAP, These are again matter energy density and baryon energy density in these units. Pretty much everything is allowed, and we are now at here. These are Planck 18 results. So we have come a long way in determining cosmological parameters. However, there is still room for improvement over there, and let me try to motivate. So what are different observations at low redshifts? I will talk only about a little bit about these observations. So these are Pantheon, which is a compilation of various surveys, supernova type 1a data. And these are basically, I think this is the DESI paper. And these are the combined constraints. And where we are today, W minus 1 is the cosmological constant, sitting right in the middle of these contours. Okay. I like to show this picture because these are supernova constraints. These are BAO data constraints. And these are Hubble parameter observation constraints. Okay. So it's basically the fact that these constraints are orthogonal to each other is giving us a very, very small range in the allowed range of parameters. Okay. So what is actually, so there are a large number of models. You pick your favorite, basically check with observations, and you say, go home very nicely that my model fits, and these are the parameters with which my model fits. What actually is being fitted by observations is the energy density, the dark energy density as a function of redshift. Now these are two papers some years apart. Again, time is in this direction, and these are two different parameterizations. The same parameterization, this is the same parameterization years apart. You can see that whatever parameterization you take, whatever cosmological model you have, is the variation of the energy density as a function of redshift, which the observations are sensitive to. Okay, and coming from here to here, pretty much whatever is the range allowed here is the prior here. Okay, so basically updated our knowledge, and this dashed line is the cosmological constant model line. So we are basically converging more and more towards the cosmological constant model. However, a little bit of phantom-like model is allowed, and a little bit of W greater than minus 1 is definitely allowed. So what kind of solutions do you have for that? One solution could be that, okay, whatever parameter range is allowed by observations, you reconstruct a scalar field model based on that. Okay. And you have a potential which will give you. It's a phenomenological approach. Of course, there will be objections that, okay, it's not a fundamental physics approach or something, but this is what we have. This is the allowed range of variation of W. This is the allowed range of value of W. And you can always construct given any expansion history, you can always construct any potential, whether it's a quintessence-like potential or a phantom potential. Okay. And it turns out, it's an earlier work, that exponential potentials do come in theoretically as the better models to explain any reconstruction. You can take the kinematical approach, which has also been talked about in the previous example. I put it in red because I will spend a little bit more time on these three approaches. When in doubt, you can always resort to modifying gravity models. Okay? However, one has to worry about not just the background expansion in this. You run into problems when you want to see the structure formation in the universe. Many of the modified gravities do run into singularities if you try to form structures in there, even at the linear level. Okay? And one wants to, whenever so I'm sorry about that. So one has to basically keep checking whether the structure formation, etc., is good in these models or not. Then you can ask the data itself, what kind of models would you prefer? Okay, so these are model agnostic or model independent approaches one can have. You see the data and you try to construct the cosmological quantities without assuming a basic cosmological model. So there are various things. People are trying out principal component analysis, Gaussian processes, which have been talked about earlier, so I removed them from my presentation. And there are also machine learning algorithms in which people are trying to train their machines into getting a cosmological model out of the data. One thing which I would like to stress is that whether revisiting statistics of the well-known data in a better statistics can give us some answers or not. Okay, so one is, excuse me, can I just take some water? model of independent approach could be that you expand your quantities in powers of the scale factor. And these are the cosmographical parameters, named parameters like jerk, snap, etc., which are higher in order in derivatives. Okay, so these are the details which I would not like to go into, but this is basically you expand in terms of h z by h naught. Okay, and you have the maximum power 3 over here, which is the allowed value, and you expand your scale factor in a Taylor series. Okay, very well, very nicely done. However, you cannot go beyond redshift of 1 in this because it's an expansion, Taylor series expansion. Where does your Taylor series, because it's a local expansion, okay? So if you want to go to BO data or XR data, which is also available at higher redshifts, one has to be careful into reconstructing these using these parameters. However, one can still, the point I want to make over here is the following, that all the parameterizations that I mentioned, W0, W1, W3, you can have any number of parameters. The current observations are not able to go beyond 2 parameters in the equation of state data. For instance, it's also clear over here, not really good. You can see, okay, so this is, as I said, any cosmology talk these days is not complete if there is no corner plot over there. So these are reconstructed qualities. So one can go a little bit beyond 1, but not much. Okay, so these are this is how h of z can be constructed using these jerk, snap parameters, etc. This is using the supernova, the Hubble data, and the BA observations combined. This is the deacceleration parameter, and this is the jerk parameter. These are examples which I wanted to show over here. Okay, so these are the basically, and you can basically these are the probabilities, and you see that there are correlations in various parameters, and over here you pretty much see no correlation. Okay, and I'll come back to this point in a bit. Now what do? You are getting more and more data. The data is becoming larger. The data sets are becoming larger, and pretty much every cosmology you have, you cannot drop any of the models so far. So you decide, okay, you ask the data what to do. So what is the traditional way of fitting cosmological parameters? You assume a model. You basically search for best fit parameters. You have some prior knowledge that, okay, my parameter range will lie within these, okay? And then you fit it with the model, and you basically update your knowledge based on the new. Okay? So that is the posterior distribution that you make. You maximize the likelihood. If you have a different model, you do the whole exercise again. Okay? So now we will ask this question: if there is any way in which I can construct a function which will give me, let's say, a Hubble parameter, which I can construct using the data that I have. Now, one method is the principal component analysis, which is a multivariate data which assumes minimal hypothesis. Okay, this is also unassisted machine learning for the people who are interested in AI or machine learning algorithms. This is one such algorithm, but in this case, we're just worried about the cosmology. So what do? So you have a basis, your basis, let's say x and y. You rotate your basis such that you align yourselves in the direction in which you have the maximum information. In other words, you align yourself in which there is the maximum variance. Okay? So this is a 1D example. So this is where you align. This is the principal component, and this is the noise in that data. Okay? So basically, the technically speaking, this just means to diagonalize the covariance matrix. Okay? And the highest eigenvalue will give the principal component, and the next one will give you the error in that. You rotate the axis, align with PC, and the final reconstructed form is what you have over there. Now these methods are like, you basically want to reduce the number of parameters. You basically set a tolerance level. Okay, this is my tolerance level. This is the number of parameters. If I can get the same information at some tolerance level with some, let's say, 2 or 3 parameters. And this is what the basic premise of this is. Okay. So we took 2 approaches. All these works are with my students and a couple of postdocs. So this is work with a student who's right now in Korea doing his postdoc. What do? So you basically expand your cosmological quantity in some bases. So we chose two bases. One is 1 minus A, and Z. Okay, and we want to see which is the best expansion fitting data. And we want to test a reconstruction algorithm. First, we want to do, we simulated the data, saw whether our algorithm is picking out the data we feed it or not, basically a validation of it, and then apply it over the supernova type 1a data and Hubble parameter measurements. We chose these two because the number of points are smaller and our computing power which we have is not that great, but okay. So we chose two methods. One is, our ultimate aim is to find out what function dark energy equation of state parameter is, W of Z. Okay. So we first is the direct approach. We expanded W in these three different things. Okay. And second is the derived approach, in which, because these observations of H of Z, and this is the luminosity distance to the supernova type 1a. So here W is a derived parameter. So we took this approach that we directly expanded the observable in these bases and constructed W over there. And obviously, now it's obvious, but at that time we were quite worried that the derived approach is better. So basically, expand H of Z. Let's say if you're worried about Hubble parameter data, you expand H of Z in the basis and fit with your run a principal component and see what you get. Okay, so this is using Hubble parameter data. This is the reconstruction of Hubble parameter, and this is using the supernova type 1a data. And these three are to show that the number of points that you retain in your expansion. Okay, and you can basically see that construction is indeed very good. What is it dependent on? It's dependent on the error bars. Okay, it's very sensitive to whether the error bars are large, and it can take the construction up or down depending on how error bars are placed in it. As you can see, if you have more data points and the error bars are and the error data is good, the reconstruction of the luminosity distance is indeed very good. And then what to do next? Okay, it's basically fitted your DL, you get model independent luminosity distance, but W is a derived parameter. So that is a caveat which one has to live with. And this is basically just to show you the three different expansions that we did. So this expansion, basically 1 minus A, gives you the best results. Is the reconstruction which comes out is best for this kind of expansion. So basis 1 minus A is good. And it's also reassuring because 1 minus A, basically you make your Taylor expansions in these variables. Okay. So, and as I said, the caveat is, okay, the Hubble parameter and the equation of state parameter is this, it's a derived thing. So there is a derivative which comes in the H to obtain W of Z. And similarly, if you're talking about supernova type 1a, you have this luminosity distance, and the equation of state parameter has a double derivative and a single derivative. And here, the algorithm goes bad. Okay. So if you claim that with completely model independent analysis we have done, and this is what we get, take it with a heap of salt, if not a pinch. Okay. So this is the problem. Now, how do you solve this problem? So we hybridize this approach. We construct this quantity in a completely model independent form, and then here we basically search which fits this as in a Monte Carlo search. And then so PC, as I said, is very effective in determining observables, the direct observable of a given data set, not effective in derived quantities like the dark energy equation of state parameter. Okay. So what do? You basically, now it's a compromise that you make. You basically search using these parameters, and you do an MC-MC search. It's a matter of detail, but we use the no U-turn sampler, which is basically a variant of Hamiltonian Monte Carlo sampler. Here you solve the Hamiltonian equation, okay? And this algorithm knows when to stop automatically, okay? And you check for the usual checks for convergence and autocorrelations in the same chain, and you see that now you can really obtain very good constraints on the value of the Hubble parameter, and this is W0, W1, this is the derivative of the variation in the, and this is the next term in the expansion. I wanted to show you this This because my student got bored of writing W0, W1 and so on, so he thought I'll write differently. So that's the only thing. Sorry about that. So you point to notice over here is that here you can still talk about some correlations and some ranges, but here you cannot talk about anything. Any value will work, okay? You may say that this variation is large, is deliberate because we have very, very large error bars in your simulated data sets. The point I'm trying to make over here is that you cannot go beyond 2 parameters in the equation of state parameter determination. Third one doesn't matter. The equation, the data is not good enough yet to go beyond this. Another way of saying the same thing is a scree plot. Okay, so basically these are the covariances which are plotted over here, and you decide where the elbow of this scree plot is, and whichever is above the elbow can basically is, for instance, here it's easier here that these 2 parameters are okay, but these are very, very small, and you can discard them in the higher orders of expansion. Even this is not that great. So basically this is dropping out almost all these parameters, and the only thing you're left with is W0. So this is one way of basically reducing your parameter set and getting a better. And this is simulated data. This is supernova. This is a union compilation data, not the Pantheon one. And you can see that this is a cosmological constant. And you can see that you can indeed get a variation of W with respect to the redshift. And this is your, whatever model you propose, better remain in these confines, is what the message of this study is. Okay, now since we have talked about tensions, let's talk about the tension a little bit. Okay, and it's just before lunch, so there is hope for retrieval. So this is Hubble tension, which Anjan talked about. These are the Planck observation values, and these are the Rees et al. So these are CFIT calibrations. For students in the audience, CFIT's variables have a period luminosity relationship, which is standard. The higher period is higher luminosity CFITs, and judging by their, you measure their absolute measured apparent luminosities, and you know their period, and you can basically find the distance because you know what the implicit luminosity should be. Problem is that the calibration relation depends on the metallicity of the star. It's very highly dependent on the metallicity of the star. Okay, but they are very good calibrators. They have been, so you basically calibrate the low redshift supernovae using a CFITs, calibrate the higher redshift supernovae from those supernovae. So this is how the Pantheon data set has been calibrated over here. This is the cosmic distance ladder, and you find this tension that the Hubble parameter which is allowed by these observations is around 73, and there is no match at the 5 sigma level. Okay. One thing which I wanted to point out is that, as Anjan also pointed out, that the central value has not shifted for low redshift observations and the early universe observations by much. It's the error bars which have reduced. Okay, and it's the reduction of these error bars getting better and better data which basically revealed this tension. Now one would like to take this approach, and this is again something which we showed, that all the low redshift observations tend to get a higher value of Hubble parameter, and the early universe observations tend to get a low value of the Hubble parameter. Early dark energy models are the ones which were proposed by Kamienkowski et al. They are very good. They may solve the problem. However, this is not the dark energy which I talked about earlier. This is one blimp which has been put in by hand. So one has to worry about how much is its height and how much is its width. And one again starts the game of some more parameters. So this was early dark energy which existed in the first 30,000 years and withered away. Of course, no motivation why. But since we are working in various models, why not? So alternate solution again is to have modified gravity models. So I will not talk about models over here. What I will say is that let's see whether we have been doing the statistics right or not, and whether there is something in the systematics or the data or the calibrations which are off. So one would like to explore that. The answer is still not there, but one would still want to understand that. There is also a recent review, which is the title H0 Olympics, which basically tries to rate different models into good, better, best kind of models over there. Okay. So there was a question in the audience whether the increase in error bars can do it or not. So this is partially your answer to is the decrease in the error bars which has revealed the tension. Okay. So now let's see. What do you do? So recently, the currently the best, the most comprehensive data compilation for supernova type 1 is the Pantheon and the Pantheon Plus, which has more than. Okay. So what is the quantity that you observe? You observe the distance modulus. This is the this is the stretch parameter, which is basically putting all the light curves on top of each other. This is the color. And let's forget about these two, but these are matter of detail over here. But these are also two parameters which you fit for this. This is the distance modulus. You fit it with, you match it with the distance modulus, which you can compute from your theory. And here your cosmology comes into the picture, H0, and the way universe has expanded over time. And for evaluation parameters, it is the chi-square which you minimize, is the covariance matrix, and these are residuals. Residuals being the difference between mu observed and mu theoretical. Now recently it was shown by Dainati et al. That these residuals, this is the diagonal, this is the covariance matrix, these are diagonal values of that. These residuals do not fulfill the Gaussianity criterion. Okay, so the distribution, which basically, and all the analysis which you do, usually you assume a Gaussian distribution in error in these deviations from these values. Okay, and it turns out that if you consider the Pantheon data, the logistic distribution, which is heavier on tails, the more kurtosis, is fitting better to the residuals, and student T data, T distribution fits better the Pantheon one. So we were intrigued by this, and we thought let's investigate this first and see what we get. So they do it in assuming a lambda CDM model. So we decided to do all parameterizations we could think of, whether that is the one which is missing in that. So we basically put all the tests which are standard tests, and if someone is interested in details, we may talk about it, the AIC tests and the Bayesian inference test, we put that, and we found that indeed the logistic distribution does fit better. You see over here that the central value shifts by a huge amount. It actually, so one sees that the error bars increase, but the central value shifted to worsen the Hubble tension. Okay, and this is using the Gaussian. One inference that we can make over here is that probably the assumption of Gaussian distribution of residuals is basically underestimating the errors, number one. But we are intrigued by the fact that the central value shifts a huge lot. And we are still working on it, not understood it completely. Okay. This is LCDM, and this is for WCDM models, and you can see that we do not get rid of any problem over here. Okay. These are assuming the absolute magnitude given by the Pantheon people. Okay. Now this capital M, the absolute magnitude, and H0 have a degeneracy in them. So basically they are measured together. So you fix one and you determine the other. Okay. So in this case, we fix the absolute magnitude and determine H0. So this is what I wanted to clarify over here. Then we thought, okay, probably if we want to see whether the low redshift data is driving these constraints, I'll be finishing too. Whether the low redshift data is driving these constraints or the high redshift data is driving these constraints. So we arbitrarily divided the data into high redshift and low redshift bits. So we decided, okay, 0.5, granted. 0.5, higher than this is high, lower than this is low. And you can see over here that the full Pantheon data is aligning very well with this low redshift data points. And all these are pretty much making almost no contribution in the constraints over here. And similar is the case for logistic data over here. Okay. Logistic analysis. This is using Gaussian, this is using logistic. Okay. Now, then we thought, okay, probably it's because that high redshift, there are less number of supernova points, whether it's the larger number of points which is making a difference or not. So we decided to put it half, arbitrarily put half. equal number of data points here and there. Now it serves the dual purpose of low redshift, high redshift distribution as well as distinction as well as more data points in both the data. And here also you can see that a particular set is driving the constraints. So one has to look at the data subsets very carefully also, and individually also the Gaussian does not fit better, logistic fits better. Okay, and then we thought, okay, this Pantheon data set is a collection of different surveys. It's not a homogeneous data set. It's SGS's data, it's PanSTAR's 1 data, and it's also Supernova Legacy Survey data. Now, among these, Supernova Legacy Survey is homogeneous. Okay, very good constraints were obtained when it had come out earlier. SGSS, of course, is what survey. Here you can see that if you assume Gaussian, they do even the same data set, they do different kinds of constraints, they are orthogonal, but there is an overlap. So one can still live with that. If you do the logistics, the SDSS completely is off from the other, within the same data set that we have been talking about. We just divided by the survey. I have not put the PanSTARS one over here yet because the analysis is still on. So you can see that this is a Supernova Legacy Survey. The full Pantheon data set is consistent with this rather than with the SGSS one. So one checks for Gaussianity of residuals in a given survey, but when you put them together, one needs to check whether they follow the Gaussian randomness or not in this case, which is not the case. The error bars increase, Hubble tension worsens. Okay. So what we did was we thought how much of change in absolute magnitude will give this. So you can see that this is 0. 0 is change from the Pantheon value, and you can see that very small change can change how much can give you an enormous amount of change in the value of the Hubble parameter over here. This is the error bars using logistic data distribution, and this is using the Gaussian distribution. So moral of this story is that one needs to do statistics very, very well also. Okay? And we are not alone in this. People are looking at these things. One is the sibling-based calibration. Two supernovae in the same galaxy are giving different magnitudes. So one needs to calibrate them, the dust, etc. correction in the same galaxy properly. And when you do that, the Hubble values come within 1 sigma of each other. So this is one place to look at. Recently, Zwicky transient facility papers, they show that the distance modulus relation, which is linear, which I showed over here, is not linear. The supernova type 1a depends on the environment it is in. The heavier red environment hosts brighter supernovae than the other one. So one wants to give this fit with these nonlinear fitting relation. And once the data is public, one should basically look at that. This is my favorite. This is RAISIN. This is the near infrared. Now, infrared observations are not susceptible to dust extinctions. And already there are only around 40 points, and we are getting very good constraints in the near infrared RAISIN survey, which is Bob Kirshner and all have been working on. Wendy Friedman recently calibrated supernova of type 1 is same data set. We are talking about the same data set. This is a new data which is still to come. Tip of the red giant branch, which has been talked about earlier also, and this is the J region, J area giant branch, which are the carbon-rich stars which are now considered to be new standard candles. And if you calibrate using these two, there is no Hubble tension, is what Wendy Friedman et al. Have been. There is already a rejoinder to this, that if you use the method by Rees, the tension comes back. So there is tension within tension also now. Okay. This is also, this is as much of a favorite of mine as this is, that if you have a high redshift anchor, if you look at BA observations and calibrate your supernova of type 1A using high redshift anchors, you do not have the Hubble tension over there. So one has to look at these also in a very careful manner. Calibration and systematics. These are the two words I would like to put in. So this is a summary of my talk, and I would end here.
Hello? Yeah. So I find it especially interesting is that when you said that you find instead of Gaussian distribution, which we mostly take by central limit theorem, you say that the T distribution you find very interesting, you and your student. So I'm just asking that I know basics of MCMC. So how the likelihood change? Because the Gaussian was the prior distribution. If we take, the likelihood is very easy and the give sampling is very easy. So could you just comment on that, like how the T distribution will change?
Okay, I haven't put the formula over here, but I can talk to you offline. That likelihood is there. And we also put, for various parameterizations, we put the AKK test, and you basically put a number, there's a number, it has to be more than twice that, and we can show that LCDM is best in some, and WCD is best in some over there. I can show
Okay,
you
okay,
that
okay.
yeah.
So the entire data is done, the priori itself is the T distribution.
Yeah. Another thing which I want to caution you about, since you asked, and it's a very good question, if I have more and more data, it will of course go towards the Gaussian distribution because of the central.
Because of this. Thank you very much.
I have also related question. So you have found that logistic distribution is more preferred over the Gaussian distribution. So how did you verify that one distribution is more preferred over the other?
Okay, so there are these AIC and BIC tests, okay, and there are standard tests in which you compare the two distributions. So basically, you have a distribution. One test is, so let's talk about KS test, okay. So you have a distribution. You basically to compare the another distribution and see whether this is a parent distribution of it or not. Okay, so you basically have a logistic formula. Okay, you see this, you basically test it using that. So I can show you the formula over there. So these two logistic and BIC and AIC tests, they check whether your distribution is how close is that to a, let's say, a Gaussian or a logistic distribution.
Yeah, but my doubt is, okay, you can consider third distribution or another fourth distribution which can give less AIC or BIC as compared to your logistic distribution.
So one also has to consider that so these two penalize you, these two distribution tests penalize you if your error bars, etc. If you put too many parameters, these tests actually penalize you.
No, that depends on the parameter. I'm asking, so if there can be a distribution for third distribution which may not be Gaussian or logistic, that can give you a less AIC or BIC as compared to this.
So then that you worry about more then.
Okay, then is there any way to pick the best distribution?
So that's where these tests come in. So we take a call, okay, this is better fitting, we will do that. But all the distributions, if you have larger and larger number of data points, will tend towards Gaussian.
Yeah,
but currently they are not.
Okay.
Your last slide was quite disputable. Tension or no tension? So your opinion.
Okay. My
Final
opinion is
is
before saying a comprehensive thing that there is a tension or not, one needs to worry about calibrations and systematics very well. If you say, okay, my data is, I have taken care of systematics, I have taken care of calibrations, and still there is a tension, then I would say, okay, yes, there is a tension. So right now I would say that one has to wait for it, get better data.
I actually have a very naive question. So at the beginning of your talk, you showed that you can basically tailor expand and go beyond the deceleration parameter. The third one would be the jerk, and then there's another one. The thing is that I just wanted to know whether the data is sensitive enough to get these parameters, or also what jerk and the other parameters physically mean. I mean, I can understand the deceleration, right? So,
how do I put it over here? So number one, the data is not sensitive to go beyond, let's say, even the deceleration parameter. They have been in place, snap and jerk, all these parameters. So basically, one also can ask where does the series terminate, right? So these you can say as that basically, I think Anjan can answer this better, he's been working. Basically change in the accelerating parameter, deceleration parameter is the next one and the next one.
Thank you.
But data is not sensitive to go beyond Q, I think, in personal opinion.
Yeah, I just want to comment, if you go to your these SDSS and Pantheon slide that you are showing, so is sometimes it's, so you know that when this, as you correctly said, the Pantheon plus, they take different observations and then they put together. While doing that, there are a lot of temple matching thing is there. So because, let's say SDSS or SNLS, right? So when they say that this is a type 1A supernova or whatever, for there's a lot of template they use, fine? And when you put everything in a single like Pantheon plus, fine? So there are a lot of correction that you have to do so that you put them in a uniform level, fine? Now, if you just take SDSS thing as it is, and then you compare with Pantheon and say that, okay, this is completely different, I don't know how you do it, but if you just do it blindly, then there is a problem, because while getting this Pantheon plus, they do like SDSS, HST, SNL, so they have all those supernovas measured from different observations.
So they use the standard salt.
So there is a light curve matching, and then you do a lot of corrections to put it in a single thing.
That's where this is.
That's why this.
This is Gaussian. There is no problem over here.
No, Gaussian logistic I am not saying. I am just saying that, just taking Pantheon and compared to SDSS may not be a good idea.
Pantheon, this is a subset of Pantheon. We are just doing the separate analysis.
When you go from Pantheon
and
to SDSS,
using the same absolute magnitude, using everything the same which the Pantheon dataset gives you, okay, only thing we have changed over is the likelihood over here.
You mean normalization of the
Normalization.
Because that changes your error bus actually.
Yeah, so we have taken whatever Pantheon has given for this. Same M.